Here we're going to set up a triple integral over a particular region, E. And the region is defined as lying between two spheres, one of radius 2, one of radius 4, and above a cone that has an angle of pi over 3 or 60 degrees. So let's start by sketching out maybe what a cross section looks like. I always feel like if we can do this, it's a really nice place to start. Helps us understand what it is that we're trying to look at. Alright, so we've got our cone, which is going to have an angle of 60 degrees. And that'll do something like this. On either side. So we're bounded below by that cone, and we're going to be between a couple of spheres here of radius 2 and radius 4. So we'll sketch in what we think that looks like. So maybe this here is the sphere of radius 2, and this maybe here then is the sphere of radius 4. So here's rho equals 2 and rho equals 4. So we want to be between the spheres and above the cone. That would put us in this region in here. So this is looking at the cross section, which means that this is the xy plane here, and this is the z-axis. Now if we look at the top down of this particular region, it's the entire sphere that we're looking at in the entire cone. So this is going to look a little bit like a donut from the top down. If we try and visualize this, you're going to have two concentric circles here that are going to represent sort of this region of integration within the xy plane. So this is again looking down on the xy plane, and this is looking at a cross section over here of what it would look like from the side view. Alright, I think from here we can figure out how to set up our limits. This was pi over 3. So we can see that phi is going to come down. In order to fill up our volume, phi is going to come down from the z-axis everywhere between 0 and pi over 3. Here's our phi. Theta we can grab from over here. We're going to go all the way around. So 0 less than theta less than 2 pi to make sure we get all the way around. And we just need rho. So this is pretty straightforward as well. We want to get all the values between the inner and the outer surface here. So again, rho being equal to 2 here, rho being equal to 4 on the outer. So we have that rho is trapped between 2 and 4. And again, phi being trapped between 0 and pi over 3. So there are our 3 bounds. And now we just want to put them onto our integral. So the integrand was xyz. Let's get our triple integral. And we'll have to convert our x, y, and z like we've typically done. So let's get those conversions up and handy. Alright, there they are. And now our integrand was x times y times z. So we're just multiplying all of these together to convert that integrand over. So when we do that, we end up with a rho cubed, and we'll get a sine squared phi, a cosine theta, a sine theta, and a cosine phi. So I'll put the cosine phi here, and then we'll have a sine theta, cosine theta. And then we need our dv. Of course, in spherical coordinates, dv is computed as rho squared sine phi, and then we have r d rho, d phi, d theta. So let's throw our limits of integration on. Rho goes from 2 to 4. Phi goes from 0 to pi over 3. And finally, theta goes from 0 to 2 pi. So there you go. We have it all set up. If we wanted to take a minute, we could just simplify this integrand one more time. Integral from 0 to 2 pi. Integral from 0 to pi over 3. Integral from 0. Integral from 2 to 4. And then we would write this out finally as rho to the 5th sine cubed phi cosine phi sine theta cosine theta d rho d phi d theta. And that gives us something that we can work on reasonably well.